Happy Thursday, Trailblazers. This is Mr. Parrish. I am speaking to you from an airplane right now, about 30,000 feet in the air. Yes, am I annoying the passengers next to me, but I don't really care. We got to learn some chemistry, so this is what we're going to do today. Go ahead and write down this bell ringer in your bell ringer sheet. This one should be pretty simple. I'm going to give you guys about 3 minutes to do this. So you have 3 minutes starting now. If you hear any weird airplane noises, I will let you know if we're safe or not. I think I'm going to be fine though. Probably. Got 1 minute left. Okay, hopefully you guys had enough time to really think through that question. It seems like an easy one, and if I had to guess, I'm guessing most of you picked this one for density. And the reason my students have given me the reason in the past they picked that is because it sounds like a good answer. It's like fancy, and I guess that's a reason to pick an answer. I wouldn't say it's a good one. I don't think most of you would have picked boiling point. I think most of you know that's a physical property. I think colorless gas, I think most of you would have known that's a physical property, and odorless gas is a physical property as well. Density is also a physical property because it's very easy to calculate. You just need the mass and the volume and you can easily find density. You don't really need to chemically test it at all. The answer is H, because for physical properties, they should be easily observed. You can easily find the boiling point of something. You can easily observe its color, its smell, and its density. Chemical properties must be tested to observe. So even though they give you the formula up here that it's methane, if you had some methane sample, you wouldn't be able to see that it was actually made of carbon and hydrogen, right? Same thing with water. If you have water, it just looks like water. It doesn't look like hydrogen and oxygen. Okay, so chemical properties must be tested to be observed, and physical properties are easily observed. Go ahead and take 20 seconds and write that down on your bell ringer. Okay, we're actually going to do another bell ringer right now. I want to go over fission versus fusion. So this one's pretty simple. I just want you to draw this diagram on the left side of your bell ringer here, and then I want you to write a sentence explaining whether it is fission or fusion. I'm going to give you 2 minutes to draw the diagram. The diagram doesn't have to be perfect, just kind of get the idea of the diagram. You can see like there's not actually like 92 protons in this diagram, but it like gives you a rough idea. Okay, 2 minutes, go ahead. One more minute. You shouldn't need your notes from yesterday, but in case you want to look at them, you can. Okay, hopefully at this point you have now figured out that this is fission. The reason that it's fission is that the nuclear change above, like you have a large nucleus breaking apart into multiple pieces, right? That is the definition of fission. Fusion would be the opposite. Like if these two came back together to make a bigger nucleus, that would be fusion. Remember, fission equals division, right? It kind of rhymes. They both end with ION, I guess. So you can use that to help you remember that fission is when things are breaking apart into smaller pieces. All right, you need to go ahead and take a look at your new packet. Go ahead and turn to page 5 in your new packet. All you need is that and a periodic table. So I'll go ahead and give you 30 seconds, take those two things out. Okay, we're going to take some notes here together, and then you guys will have most of the class period to practice and study for tomorrow's quiz. Your homework tonight is page 7 of the Unit 4 packet. If you complete that, that will put you in a very good spot for the quiz on Friday. So let's go ahead and get through it. We're going to talk about nuclear decay equations today. All right, if you remember from yesterday's lesson, there are 3 types of decay, right? Alpha, beta, and gamma. And when we get those kinds of decay, we can actually use them in what are called nuclear decay equations. Okay, so you're going to need this chart from yesterday's notes in order to answer a lot of the questions. So I'll be referencing this slide back and forth as we continue working. In a nuclear equation, the sum of the mass numbers, so the numbers on the top of the equation, must be equal on both sides. So you can see in this equation you have 9 and 4, and down here you can see the math. 9 plus 4 is 13. And on this side we have 12 and 1, so again it must be 13. Right, the atomic numbers must be the same on both sides as well. So this is 4 and 2. See down here 4 plus 2 is 6, and then 6 and 0. So 6 plus 0 is obviously 6. Right? They must be the same on both sides. You learned a little bit about this from 8th grade from the law of conservation of mass that said that basically like matter is never created nor destroyed. So on the left side it should be the same as it is on the right side. And even if we're missing one, like if we were missing this neutron, we could actually figure out what these two numbers should be and then figure out more information from there. Alright, so in this example, we have thorium-234, and it's undergoing alpha decay. I know this is alpha decay because this is 4/2 for helium, right? So if I go back to this slide, I can see here this is alpha decay right here, 4/2 helium, or it could be 4/2 with an alpha symbol. Alright, so we have to figure out the missing nucleus. Well, I don't know what the missing nucleus is yet, but I have a lot of information. I can start with the mass numbers. I know this side it's 234, so that means this side must be 234 as well. So 4 plus what would give me 234? Hopefully you said like 230, right? So 230 is actually going to be the mass number in this scenario. For my atomic number at the bottom, I know the total has to be 90, so 2 plus what gives me 90? Hopefully you said 88, right? So 2 plus what gives me 90 should be 88. So now that I know my mass number is 230 and my atomic number is 88, I can look at the periodic table and I can see that element 88 is radium. So my missing nucleus in this case would be radium-230. So all I did was just use the law that I mentioned earlier about how the mass numbers need to be the same on both sides and the atomic numbers need to be the same on both sides. Let's try another one, shall we? Okay, here we have carbon-14. And it's undergoing beta decay, and again I know it's beta decay because it's losing an electron here. So when I go back to this slide, I can see beta decay here is 0 and -1 for an E for electron, or 0 -1 in the B for the beta symbol. So we're going to go back, forward. Okay, so now I know that my total has to be 14 for my mass number. So 0, and these are just variables, A, Z, and X. They don't actually have like any meaning. You could just, like in math, you solve for X, so these are just variables. Okay, so I know 14 has to be the mass number. So 0 plus what gives me 14? Hopefully, again, you said 14, so that's going to be my mass number in this case. And for the atomic number, we have 6 on the bottom. So this one's a little trickier because you have a negative symbol here. So I like to think about it this way. Right? Z minus what will give me 6? Sorry, Z minus 1 would give me 6. Right? So Z must be 7, right? So in this case, our atomic number is actually increasing, not decreasing. And if I look up on the periodic table and I want to find atomic number 7, I can see that it's nitrogen. So this would be nitrogen-14 is my missing nucleus in this case. Alright, let's do one more example, then you guys will have a few minutes to practice. Alright, so here, this one's a little different because this 3, the coefficient in front of the hydrogen, is actually going to get distributed. So the 3 is going to be multiplied by 1 here, and the 3 is going to be multiplied by 1 here. So my mass number in this case is actually going to be 3 plus 9. So 3 times 1 is 3, plus the 9 gives me 12. Right? And now I know that this side has to equal 12 as well, so I have an A here and then a 4, so A plus 4 should give me 12 as well, so A should be 8 in this case. This is actually a very uncommon example. This will not be on the quiz tomorrow, but I just thought in case it got thrown your way on a common assessment, you have seen it before. So now we're going to do the same thing for the atomic number. Again, the 3 is going to get distributed to the 1, so 3 times 1 is 3, 3 plus 4 is 7, so now I know 2 plus what gives me 7? It should be 5. So now my atomic number is 5 and my mass number is 8. So I look at the periodic table and I need to find element number 5, and that would be boron. So this is boron 8 in this case. So just remember, the mass number on the left needs to be the same as the mass number on the right if you're adding them together. These are all examples of transmutation reactions. I mentioned this word yesterday in the Venn diagram, but I just thought I should bring it up again. In most chemical reactions, you don't change the identity of the element, but in this case you are. Like, look at this example. You have thorium here, and then on the right side you have helium and radium. Those are completely different elements. These are the only types of reactions that actually change identities. Okay, turn the page to page 6. And we'll start, and in the next video we will talk about nuclear decay equations. I'm sure you guys are doing a great job. Thank you for being so respectful to who's ever in the room and learning so much chemistry right now.